Hi and welcome to another video where we're going to be exploring more about limits, and specifically we're going to talk about limits in terms of how it relates to rate of change. But first, we're going to watch this little video, and you'd be amazed at the things you can find on YouTube. I think there's a video for everything, including a couple of guys who just randomly throw a rock off a bridge. Now, disclaimer, I do not encourage you to do this. I know that there are some channels out there that have done this in the past. And just to be clear that they make all the arrangements they need to ahead of time to make sure that everything they're doing is legal. Now, I don't know if these guys did anything legal or illegal, but I do not condone dropping rocks off of things unless you have made arrangements and ensured that all safety precautions have been made. So with that disclaimer in place, let's see what's going on here.
Oh my God. That's it, we're out of here.
Now, that was just some random video that I happened to find, and it suited our needs because, wouldn't you know it, I have a problem about dropping a rock off of, the top of something. And we're going to use this as our example. Now, in the description to this particular video, the guys who threw this rock over the bridge and into the water below claim that it fell a distance of 467 feet. Now, we have a start time, we have an end time for some of these things. So as we start looking at what's happening in these scenarios, we're going to make a couple of assumptions here. Assumption number one, we're going to assume that the rock was dropped with an initial velocity of 0 feet per second. It wasn't pushed, shoved, it had nothing other than gravity acting on it from the get-go. We're also going to assume that wind resistance is negligible. In other words, it's too small to affect our calculations. Now, I know very well from a physics standpoint that wind resistance is always something to take into account. But for this short of a drop, the effect that it'll have on any calculations that we are going to make are going to be very small. We are also going to assume that these guys didn't break any laws in dropping the rock off the bridge. So fingers crossed. On Earth, the equation for the distance in feet an object falls after t seconds is found by using this equation. And we'll see a little bit more about where this equation comes from. You might recognize that number 16 as being involved with the coefficient, the gravity coefficient for Earth. So we also have one for meters per second that you may have learned in physics. And we're going to have an opportunity to see maybe where some of these physics equations that you have used in physics class have come from. Because after all, physics and calculus go together, as Isaac Newton influenced both quite heavily. So question number one that I would like us to consider here, and I've got three of them. The rock takes approximately 5 seconds to fall. So if you rewatch the video, which we're not going to do, you'll have to take my word for it. It takes about 5 seconds to fall. So from about 14 seconds to 19 seconds in the video. The guys in the video claim that the rock fell 467. Does our equation match with this assertion? So let's set it up and see if things make sense. So I'm going to set up my equation, remembering that y is the height. So 16 times the time it takes to fall gives me 16 times 25. That's about 400 feet. Now, it's not exactly 467, but this leads me to believe that if we were to take a more precise measure of the time it took to fall, that we might be pretty well within 467 feet. So I do believe that it is believable. So now question two, use the slope formula to estimate the average speed of the rock during the first 2 seconds of its free fall. So what we need to do is we need to say, well, the beginning point that we're going to start with is 0, 0. So at time 0, it has fallen 0 feet. At time 2, we need to plug 2 in. So I'm going to go over here. Y is 16 times 2 squared. That's going to be the 0.64. So it's gone about 64 feet in the first 2 seconds, according to our equation. Now remember, these are all estimations. We probably have some other physics things going on, but we're going to make some basic assumptions just to keep the math a little bit simpler. So the average speed during the first 2 seconds can be found by taking the slope between these 2 points. So 32 feet per second is the average speed of that rock. Now, we all know that an object that falls towards the Earth is actually accelerating at the acceleration rate due to gravity. And on Earth, that's 32 feet per second. We also know that, on other planets, there might be different gravitational pulls. But that's the acceleration due to gravity. And so this rock is actually accelerating as it goes towards the ground. But between 0 and 2, the average velocity, the average speed, because remember velocity is directional, the average speed of my rock as it falls is 32 feet per second. Now it goes from 0 to 64. So, or 64 feet, but on average 32 feet per second. So now question 3, what's the average speed from time 1 to 2? Well, okay, so now we need to find 1. So when I plug in 1, I should get 16 in my equation. So I need to now find the slope between these two. So here we go, 64 minus 16 over 2 minus 1 gives me 48 over 1, 48 feet per second. Now this should make sense that because I started from 0, if I were to take the average speed now from 1 to 2, it should be higher because it's accelerating. So let's keep going with this. From 1.5 to 2, 1.5, and I'm going to need to plug this one in and get my decimal value here. And as we crunch those numbers and plug them into our slope formula, we end up getting that our average speed from 1.5 seconds to 2 is going to be 56 feet per second. Now, what's happening here? Well, as we approach that instant of 2 seconds, we're finding average velocities, and we're closing the gap and squeezing in, if you will. And if we take a look at the graph of what's happening, we're going to see that as we approach that number 2, we actually begin to approach a certain value. So let's take this one more step here, 1.75. So let's see, 1.75, and I'll find that value, 264. What happens when I find the average velocity over that quarter of a second? So here over the quarter of a second, the average velocity is 60 feet per second. So we've gone up from 32 to 48 to 56 and now to 60 feet per second. So we're getting faster and faster with our estimation of that average velocity. And I would wager to say that if you wanted a snapshot of what's happening right at the instant of 2, that if we kept closing that gap, and suppose instead of making it a quarter of a second, maybe we do a 1/10 of a second, or a 100th of a second, or a 1,000th of a second. And if we found the slope between those 2 points, we could get very close to approximating what is happening at the instant of 2 seconds. And so let's jump into the theoretical realm here, and let's take a look at what's happening in the graph. So I have here an image of a situation in Desmos, and you can see that I have plugged in our equation, y equals 16t squared. I've labeled the point 264 because that's the blue spot here. That's where we're trying to estimate. And I've created a movable point. So this point's going to move. This is the point we're trying to find the slope between. And so if you look down here, the very last one in box number 5, this is the slope between my movable point and the time 2 seconds. And you'll see right here at this instant, wherever A is, whatever this point is, at 1.93 seconds. So we are 7/100ths of a second below that spot. We're just approaching the 2. And look, the slope there, that equation, that average velocity is about 63. So I'm going to hit play, and I just want you to observe what's happening. It's going to bounce back and forth a little bit, and I want you to pay attention to this number right here in the bottom, this M number. There it is. It goes from 60. Oh, it hit an undefined spot. Oh, it goes back and forth between 65, 63, 62, 63, up, undefined, 64, 65. And if we were to make a guess and to say, well, it's undefined at that instant of 2 because in our slope formula we get a 0 in the denominator. We also get a 0 in the numerator. And this instance happened to us in a previous video where we talked about this concept of a limit. And when we have 0 over 0, how we call that the indeterminate form of a limit. And what I want you to understand and connect here is that what we're trying to find here is actually a limit. As that point gets closer and closer, as we close the gap, as the distance between the point in question and my movable point approaches 0, what is my average speed approaching? That's why this is a limit problem. And so let's name a few things. Let's name the distance between my movable point and my point in question. We're going to call that distance h, because ultimately we want that to be 0. But it's never going to be able to be 0 because we would never be able to find the slope. So the idea here is that we're going to name this difference between my point and the point, that movable point. That difference is now going to be called h. And as h gets very, very small, let's see, we've got our point 2 and 64. As h gets very, very small, we're able to estimate and find the limit of that function, and we're able to find the average velocity. So we're going to call the x value 2 plus h. So remember, h is the difference between 2 and that movable point. So that's always changing, right? So h plus 2 is my second point, which means then we need to plug in f of 2 plus h. Now, I'm going to remind you that 64 was just f of 2 in that 16 equation. So f of x, or f of t, whatever you want to call it, is 16x squared. So the idea here is that my average is going to be f of 2 plus h, so the two y values, it's the slope formula, minus f of 2 all over 2 plus h minus 2. Now you'll notice what happens here is the 2's will cancel out on the denominator. So we end up with this, f of 2 plus h minus f of 2, that's the 64, all over h. Now that's your average speed. The problem is we want h to approach 0. And if h is equal to 0, we get that 0 over 0 indeterminate form. So what we need to do is think about this in terms of being a limit. And once we establish that it's a limit as h is approaching 0, not actually equal to 0, but approaching 0, then we can use some of those limit properties where we can simplify, algebraically manipulate things, and we can actually evaluate the limit. We can't evaluate this thing yet because it's just got this h, and we want h to be 0. So what we're going to do is we're going to turn this into the limit as h approaches 0 of f of 2 plus h and what this is going to give us is the exact moment of 2 seconds. What is our exact speed right at 2 seconds? How fast is that rock falling at the time 2 seconds? Now we call this the instantaneous speed. So let's kind of recap what we're doing here. We've got average speed, which is the slope between any 2 points. We have now the instantaneous speed, which is the only way you can find that at this point is to express it as a limit of 2 points that I'm finding the slope where the distance, h, between the 2 points is approaching 0. So here's the information we need to know. The average speed, you can think of that as point A to point B. You've got f of b minus f of a, or in this case y of b and y of a. You plug those in, and you find the slope between the 2 points. That'll give you the average over an interval. Averages are always found by taking the slope between the 2 endpoints of the interval. The instantaneous speed at an exact moment in time is found by evaluating this limit. Now in the previous example, we found the time at exactly 2 seconds. Here, this is a general form, and this you're going to want to write down, and this is going to be a really important thing to have in our notes. And what happens is it actually simplifies to having just h on the bottom. So you can always cancel out the a and the minus a, and you'll always have h in the denominator. And the only way we can evaluate this is through a limit by algebraic manipulation. So let's apply this, and we're going to find the instantaneous speed, there we go, at the time t equals 3. So let's find a few things. So first of all, here's my equation, 16t squared, and now t is going to be 3. So the distance that I have fallen is 16 times 9. And so I've fallen 144 feet at that instance. And so now I'm ready to set up my limit. Now to find my limit, here t is 3, so this is the a value right there and right there in my equation. So what I actually need to do is I need to evaluate f of 3 plus h. And so if my equation is 16t squared, I need to plug 3 plus h in for t. So this is 16 times 3 plus h squared. This is a composition of functions right here. I'm putting 3 plus h in for my equation right here, in for the variable t. So this is what I need to plug in to the numerator. So let's write it out. So I'm going to find the limit as h approaches 0 of 16 times 3 plus h squared minus, and then f of 3, that's the a value, remember, minus 144. And then I'm just going to let the a's be canceled out. They're going to cancel anyway, all over h. Now, if I try to plug in 0, I'm going to get 0 over 0. Every single time with this particular problem, you're going to need to do these following steps. So the next thing I'm going to do is I'm going to multiply things out. Now, when I do limits, it's important to write the limit in the first step, and it's also to come back around and write it. You have to write it in the last step as well. So in the middle, when we're doing all this algebraic manipulation, it's perfectly okay to drop that limit notation throughout this middle, but always bring it back again in the end before you write your final answer. So let's take a look at what's going to happen. Now, I need to multiply out the 3 plus h squared. So I'm going to come off to the side, and I'm going to write 3 plus h squared. I'm going to write it twice and use that distributive property. The number one mistake that I see my students making in a problem like this is you take that exponent and you just want to square everything inside. You have to write it twice and distribute. So 9 plus 3h plus 3h plus h squared. So now I'm going to come back over here and I'm going to say, well, 16 times 9 plus 6h plus h squared minus 144 all over h. I'm leaving the limit notation off. That's perfectly fine. So now I'm going to distribute. I'm going to do some simplification and see what happens. 16 times 9, oh, that's 144. 16 times 6 is 96. Oh, look at this. Isn't this beautiful? 144's go away, and I'm left with 96h plus 16h squared over h. And if I try to take that limit, I'm still going to get 0 over 0. So what I'm going to do is I'm going to factor out an h. I get 96 plus 16h all over h. Those go away. And so now here's where I'm going to bring back my limit notation. Notice, I'm not saying there's no equal signs. So I'm going to draw a line. Here's all my work on the left side. My limits are going to stay on the left. So now I'm going to say the limit of 96 plus 16h as h approaches 0. When I put 0 in, I get a value. That's okay. Remember, we always start by trying to plug the number in and see what happens. So here I get 96. Guess what? That's the speed of the rock at the instant of 3 seconds. 96 feet per second. So you might be asking yourself, wow, do I have to do all of that every single time? And the answer is yes, for now, you're going to have to do this. And let's just suppose that you're coming back through calculus again a second time, and maybe you're doing this as a review for moving on to Calc 2 or Calc BC. Yes, you will need to do all this if you're in my class as a student. I make my students do this all throughout Chapter 2 until we learn a shortcut later on in Chapter 3. But no skipping ahead. I would expect to see all of these steps written out. Now, the last question on here says, suppose the rock does fall a distance of 467 feet. How long until it hits the ground? What is its velocity just before it hits the ground? So if we fall a distance of 467, we've got 16t squared. So I'm going to divide everything. I'm going to solve for my time and see how long it took to hit the ground. And so as I solve for t, here are my steps, and you'll notice I went to beyond 3 places while working inside of my work. Always go to at least 6 decimal places within your work. The only time you should ever round is at the very end. And as a matter of fact, if you're using a calculator that saves decimal values, you should just use that answer button or arrow up and enter the entire thing into your calculations. Every time you round, you introduce round off error. And so your final answer could be off. And remember, your AP graders are going to be grading decimal values up to the first 3 places, rounded or truncated. So really, you don't have a lot of room for error. If your other numbers are off a little bit, that's fine, but you have to be accurate up to 3 places. So do not round until the very, very end. So here's the time that it takes. So I want to know what is its velocity at this time. So I need to find the instantaneous velocity at 5.4025456962 seconds. So we're going to use that limit notation. We're going to say the limit, and I'm going to call this t, we're going to give it a subscript. So I'm going to call it z, because z is the last letter of the alphabet. So if you define your variable, you don't have to write that letter over and over again. So the limit as h approaches 0, it would be f of tz plus h minus f of tz all over h. So now I'm going to plug things in. Here we go. F of tz plus h is going to be 16 times tz plus h squared. So I'm going to write out, and I'm going to multiply that out, tz plus h times tz plus h. So I get 16 times tz squared plus 2 tzh plus h squared. When I distribute my 16 all the way through, I'll get this fraction here. I'll get 16t squared plus 32 tzh plus 16h squared minus, now f of tz is just 16 times tz squared all over h. And as I simplify, these will cancel out. So I'm going to have 32 tzh plus 16h squared all over h. I'm going to factor out the h, and it'll go away. That's the beautiful thing about these problems. They always kind of follow the same pattern. If you can get yourself started, it usually ends the same way every time. So I'm going to have 32 tz plus 16h all over h. These go away. And so now I'm going to come back over here, and really what I'm evaluating is the limit as h approaches 0 of 32 times tz, that's that 5-second number right here, plus 16h. Oh, it's just 32 times that tz value. Or if we plug it in, now we can plug the number back in and evaluate, and we can get our actual decimal. And we get about 172.881 feet per second. So when it hits that water and it hits the river below there, that's the speed of that rock. And so you can imagine that would be a pretty dangerous thing to do, to have a rock hurtling down on somebody from at 172 feet per second. That's a very, with that mass, that's deadly. So I hope this has been a good little introduction for you. I want you to not feel overwhelmed by anything we talked about in here. This is an introduction. So if you're not mastering this skill yet, don't worry. It's going to come back around later in this unit, and we're going to see it again. So this is an introduction. Remember, introduction means you don't have to get it 100%, but I want you to try it. So you're not off the hook for that. So give it a try, and just know that I'm here for you, and you can do this. Don't give up. You've got this.